Hi, everybody. So, this is the first lecture in our category theory crash course for quantum formalism. You guys maybe met me last week. My name is Brian Hepler. And so, I want to kick off our first lecture, which is going to be on the subject of categories, functors, and naturality, whatever that means, that last word, with a quote. So I included some references in the Discord channel for category theory. This is from the article on a categorical manifesto by Joseph Goguen. I think that's how you say his name. And it's sort of a pithy way of understanding how we're going to approach this subject versus how we might have approached a subject like, say, learning set theory before we learned group theory. To understand a structure, it's necessary to understand the morphisms that preserve that structure. So for category theory, for us, say sets are just as important as functions between sets. Groups are just as important as group homomorphisms. Likewise, vector spaces over some field, linear maps between them. Oops, my handwriting is terrible. Topological spaces. And continuous functions. So I'm going to abbreviate functions with F apostrophe N if you haven't seen that before. Let's see, what else? I could have posets, partially ordered sets, and order-preserving functions. And lastly, well, there's not really lastly, but kind of what we'll get to in the end of this talk is categories themselves, whatever those are, and functors between categories. So a theme you'll see here in this video and many other videos is it's very example heavy. The power of category theory is in understanding how to apply it. And part of understanding how to apply it means recognizing when you're seeing kind of categorical principles in action. So there's going to be lots of different definitions, which aren't really that hard to grasp in and of themselves. It's really in understanding how to apply them is the powerful tool here. All right, so maybe I can think about this as sort of the other way around, where categories and functors are sort of a penultimate version of understanding these things. Likewise, we could do topological groups and continuous group homomorphisms, or Lie groups and smooth group homomorphisms. There are many different things within this avenue. So maybe when you first start learning, vector spaces in linear algebra, could you imagine learning about vector spaces if you didn't learn about matrices and how to write functions between vector spaces? The perspective of category theory is that these two things are just as important as the other. So maybe let's define what a category is. These are all examples of things comprising categories so far. So, definition first. A category. You can give a really loose definition, and we'll give like slightly more precise definition. Is so loosely, a collection of objects and a collection of arrows or functions between them. Oops, that was weird. Sometimes we'll call these morphisms between them. Between objects. So this is our first very loose definition. So here, you can think about, right over here, these are objects in each example, and these are my morphisms. So for my category of sets, which I'll write as sets with an underline, my objects are just sets. My morphisms between sets are functions, ordinary functions. Likewise, for groups, my objects are groups. And my functions between groups, or my morphisms between groups, are group homomorphisms. And so on. So I'll abbreviate this. GRP underline, or vect underline. Maybe if you care about which field you're doing, you'll give a subscript for the field, subfield K. Sets. And so on. There's even a category of categories. You have to be a little bit careful about certain things when you do that. Sometimes this is a category of small categories, but that's not really important for us right now. So this is our loose definition. It's very much a nice intuitive idea of what's going on here, but we should be a little bit more precise and give the correct definition. So first off, we're going to have a set or a collection. Sometimes this is not really specified. This is sometimes called a class of objects, which I'll write as ob. So maybe I'll call this category script C. So this is a set of objects. Sometimes we might worry about this being like a class or a proper class of objects if you're worried about set theoretic issues in terms of size. But that's not a consequence or a problem that we kind of will encounter in this class so much. So for us, we can think about this as just like a set of objects. 2. So a collection of morphisms between objects. So for any two objects, let's say X and Y in C, there is a set of morphisms between X and Y. So I'm going to denote the set of morphisms by hom sub C between X and Y. So this is my set of morphisms from X to Y. So sometimes we will call these things, instead of calling them morphism, we'll call them arrows. And we'll represent this thing maybe diagrammatically as, make sure that looks like a Y, like this. So if F is some element of this set of morphisms. So a lot of times we can represent categories as sort of graphs, which we'll see a little bit later. And this is sort of the first, step toward looking at them that way. Right, so we've got a collection of objects and a collection of arrows between them, or morphisms between them. And they're subject to some sort of really reasonable compatibility problems, like where we want these things to behave how we think about functions in the usual case. So this is my first two properties. So the third one is functions or morphisms or arrows should compose in a nice way, in the way we're sort of used to. So if I've got three objects, say for any three objects, say X, Y, and Z in C, there is a function called composition of functions. There exists a function. So if I have a function, let's say, let's write it first. So imagine I have a function from x to y, and then I have a function from y to z, called g. Usually, whenever we think about functions in the usual case, I can compose these things to get a function from x to z, which I'll call g of f. This is the composition. So I want to make this thing precise in terms of my notation here. So if I have any three objects, x, y, and z, like before, I have a set theoretic function. So I take any morphism from x to y, any morphism from y to z, and it should produce, so if I take, say, some f and some g, I should be able to produce a function from x to z. So think about this as I take something like this, something like this, and I can compose these to get a function from x to z called g of f. And I write this as an actual function because by our assumption, each of these things are sets. They're sets of morphisms. And so I'm describing a function between sets in this case. In some categories, you can make these things more, nice. You can, instead of having sets of morphisms, you can have groups of morphisms. For example, like the set of linear maps from Rn to Rm, say over R. This is itself a vector space. This is the set of m by n matrices, right? Make sure I got that right. Space of matrices, which is itself a vector space. So in some nice cases, you can kind of enrich these things to get more structure here. The fun part of category theory is that there's always some other way to interpret something. Okay, so that's one of our compatibility issues. Yeah, right, this is, so the compatibility 1. Oop. Another compatibility that makes things behave like we'd hope them to in any reasonable setting, whatever that means. So I want function composition to be associative. That'd be kind of nice. So function composition that we just defined is associative. So that means if I've got any pair of triple of morphisms, say like h of g of f, I want to be able to unambiguously interpret this thing. I should be able to group them in either way, like this, for any pair of morphisms, or triple of morphisms. So maybe I've got like x to y to z to w. So. Oops, H. I want to be able to unambiguously interpret what it would mean to compose two different morphisms together. Which is pretty nice. It's something we're sort of used to in most cases we've ever encountered. And the last thing we want to stipulate is, so the last thing is 5. The existence of identity morphisms. There's a function that does nothing. So for any object, there's some function, which I'll call like identity x, or maybe sometimes I'll write it as like a, you know, 1, it's supposed to be like a bold 1, x. Which does nothing to x. So how do I phrase that? Well, an identity, let's see, all I really know are my morphisms, and so instead of thinking about how would I write, say, the identity property for an element in group theory, I'd write something like this. I'd say for any element G in my group, this is true, right? For any G in some group big G, or, you know, dot represents my group multiplication and E is my identity element of the group. So I want to stipulate the same kind of idea, but all I really know in this case are my functions. So instead of talking about things within a group, I'm going to talk about things in relation to other objects in my category. So I'll say, for any function, any function from x to y for y, some other object in the category, we have the following criteria. So any f going from x to y, and maybe some g going from z to x, we have the following properties. F composed with the identity on x is f. So if I do something, do the identity morphism that the set x or the object x first, and then apply f, it's the same thing as just doing f. And if I take my morphism g, it's the same thing as writing, you know, doing g and then applying the identity. These are sort of equivalent ideas. And later on, we'll actually see a way of interpreting groups as a category with one element that actually sort of makes this idea exactly equivalent. It's pretty cool. Okay, so this is what a category is. The first two are the sort of our main two properties, and the rest is bookkeeping to make sure that things behave like we'd expect them to. I'm sure that maybe there are some, you know, obscure types of objects where are categories where you sort of forget some of these extra compatibility assumptions, but for us, we're not going to really worry about those at all in this course. So, main definition and then some compatibility definitions. I want to take a second to talk more about this sort of arrow idea. This gets us into a really useful technique called working with commutative diagrams and categories. So in terms of commutative diagrams, whatever these are. So commutative diagram is just a collection of functions or arrows. So I kind of use arrows, functions, and morphisms, this language interchangeably. And that's really how you should eventually think about these things. So my notes. So when I looked at this composition rule here, what I said was, if I have a function from x to y, f, and a function from y to z, this composition rule said that there's another arrow from x to z, which we call g of f. And so if I say this diagram commutes, so this diagram commutes? I mean that if you can first go from x to y, and then from along via f, and then from y to z via g, it's the same thing as going from x to z via g of f. It's a sort of way of specifying equality of compositions of functions. So maybe let's try looking at some of these other rules in terms of these commutative diagrams. Some people like this because it helps you specify these criteria without going into all this extra detail about objects and set functions and everything. You just say, given anything of this form, this diagram will always commute. It's a slightly more compact way of phrasing the same language. Okay, so let's look at, say, composition of functions being associative. So I've got a picture like this. I've got my f, g, and g of f. And I've got a function from y to z, and then a function from z to, say, w, which we'll call h. By composition of functions, I know that I can write a function from x to z called g of f, and I can also write a function from y to w called h of g. So property 4 here says that if I first do, so let's write, let's say what the first thing says. So h of g of f. I guess it's on the right side. It says if I first do f and then do h of g, it's the same thing as doing g of f first and then doing h. So saying this diagram commutes means no matter which path I take to get from x to w, it doesn't really matter. The functions will be equal either way. And for the identity property, we can do the same thing. So I'll do, let's say, I think I had a function from z to x, which I called g. I have a function from x to x, which I called the identity. So this is, so the identity composed with g. And I also had a function from, let's say, x to y. Oops. How do I want to phrase that? Yeah. Here. And this is f composed of the identity. Again, this is just saying that this diagram commutes no matter what f and g are, is a different way of expressing these two equalities here. Likewise, this diagram over here is a different way of expressing this equality, no matter what f, g, and h are. It might seem a little bit contrived now, but sometimes it's easier to draw these pictures, these commutative diagrams, than it is to express things in terms of these equalities between compositions of functions. It really depends on the case. Okay. So with that in mind, I'm going to make one more definition. Well, I'm going to make lots of definitions today. But the next one I'll make is, when do I consider two objects in a category to be the same? When are they the same? Well, depending on what subject we're coming from, sometimes we'll say two groups are isomorphic, two topological spaces are homomorphic, two sets are in bijection, and so on. There are a lot of different ways we've seen this problem. understanding on two topological spaces are are homomorphic is one of the central problems in all of topology. How do you classify things up to isomorphism or homeomorphism? So let's make a definition. So I'll say a morphism, or two objects say x and y of C are isomorphic if the following happens. If we can almost, repeat this by rote, given what we know from, say, group theory or topology or set theory. If there are a pair of morphisms, if there exists a pair of morphisms, say, I'm going to write this as follows. So I'll write a function here from f, x goes to y via f, and from y to x via g. So if there's a pair of morphisms, f and g, such that the following happens. Such that, well, if I first go from x to y and then from y to x, so it's like this, it's the same thing as the identity on x. Likewise, if I go the other way around, it's the identity on y. So if that's the case, we call two objects isomorphic. Sometimes we'll also say, if you have some morphism, you say this is an isomorphism if there exists some function g that goes backwards and has this property. Occasionally, we'll also write, in this case, like g is f inverse, or so on, etc. This gives us that powerful idea of understanding sameness in different categories. Okay. Let's say, I think I'm going to, right. So now we've seen a bunch of different categories so far. Some examples have been so I've got my category of sets, which I write as set underline, or if I could write in bold, I write it as, all bold letters. Category of groups. We also have the category of abelian groups. We have a category of topological spaces and continuous functions. We have a category of vector spaces over some given field. We can have a category of fine dimensional vector spaces. People write this as FD for fine dimensional. We have given any, I'll write that as the next example. So we also have, say, monoids. We have metric spaces, topological groups, and so on. So you'll see there's kind of a notation that's kind of common, is taking the first three letters of the word and turning it into its own name for category. There's kind of an apocryphal story of a paper that needed to work with the category of, Banach analytic manifolds. And so, naturally, as one does, they abbreviated the category of Banach analytic manifolds to Banana Man. As one does. Unfortunately, mathematicians are pathologically silly, and this was published. Okay, here's a fun example, sort of an easy way of generating a category. So, take any category C, let C be a category. I can form its opposite category in a following sort of trivial way. It's opposite category, which I'll write as C op, is the following. So I take its objects are the same as the original objects. And for any two objects, x and y, the set of arrows between x and y are exactly the functions between y and x. This seems dumb, but all I'm doing is saying, so here's x, y, and f. The opposite category just says, no, the morphisms all just go the other way. So this is maybe in C op, and this is in C. This will be a little bit more useful later. It's just an interesting example of generating new categories in a way that you can say, if you have a category, if you have, say, let R be some ring with unity, and I have a category of modules over that ring of, say, left modules. So this is my category of left R modules. There's a category of right R modules. The category of right R modules is the opposite category. So this isn't necessarily just some kind of trivial, like, fun thing you can do. This actually ends up being a very useful construction. This happens in something I do all the time in the context of, say, D modules. Where, for me, D is the sheaf of linear differential operators. With holomorphic coefficients. On a complex manifold. Modules over this ring let me do things like differential equations from an algebraic perspective in the context of category theory. And unfortunately, this is not a commutative ring, so you have to care about right modules and left modules over this ring. So this is actually kind of a non-trivial distinction. But maybe more on that in several lectures from now. Let's consider some more examples. Let's play around a little bit more with this. We've introduced this pretty abstract machinery, so let's play around and see how this conforms to things we already have experienced before in set theory. Water went up my nose. Okay. So what I want to start getting you guys into is experiencing certain properties of sets or groups or vector spaces in terms of this categorical framework. So, let's say example. So we're going to work in the category of sets. And I'm going to consider a certain distinguished object of this called the empty set, which I'll abbreviate by sort of this circle through us with a slash through it, a phi. This is my empty set. Okay, so this is characterized by the following property. This is saying that for any set, say X, the empty set is a subset of X. This is the defining property of the empty set. No matter what you start with, the empty set is a subset of that set. How can I understand this thing categorically? So let's see. Well, for any such x, I can phrase this as there's always a function. There's a unique function from this set into any other set. For any x, there's a unique arrow from the empty set into x, given by, not sending the empty set to anything. You can also, furthermore, say the following. You can say the set of functions from the empty set to x is only, maybe I'll write this as like a little I or an iota, consists of only this one function. I can write it as sometimes this is actually good notation here. We'll write like this, right? Like an inclusion. We'll have like a little hook on the end of the arrow. If you're in LaTeX, this is literally like hook, right arrow. Right, I think about this function as really like an inclusion. And this is just expressing the fact that there's only one way to send nothing to nothing. So I can say that the empty set is characterized by this property for any set x. So the first exercise is here. Exercise 1. Show that the empty set is the only set with this property. Up to isomorphism. In the sense that if I have any other set that has a unique map to every other set, then it's actually isomorphic to the empty set. Up to isomorphism. All right, so I'll phrase it one more time, more specifically. So if y satisfies this property for any x, then y is isomorphic to the empty set. So I'll use this sort of like wavy equality sign for isomorphism. Isomorphic. Okay. And related to this, we're going to have another sort of example. So I'm going to take, example. I'm going to take the idea of something called a singleton set. So the singleton set. Sometimes I'll write it as just like, a little like asterisk here. And a singleton set is just a set containing only one element. So this is a set containing only one element. Okay. So here's the question. Obviously, when I write down the empty set, it is pretty obviously sort of unique in this way. You know, it encapsulates the idea that there's nothing in the set at all. But I can very clearly make, different types of singleton sets. I can say, well, here's a singleton set containing the letter A. I can also make a singleton set containing the word chair. I consider this to be like one element. It has only the one element, and that element is chair. I actually claim that these are isomorphic. These are the same set in the context of category theory. How is it different? Like, are these different in any meaningful way? So here, I'll call this capital A, and this is, let's say, capital B. After all, I can define a function from A to B that sends A to chair. I can define a function from B to A that sends chair to A. And very obviously, the composition of these things obeys the rules of an isomorphism. This gives me an isomorphism between these two sets. So we don't really consider these things to be different sets. So that's why I wrote the singleton set. Even though I can write different things in there, they all have sort of the same property. And sort of this isomorphism I constructed is sort of a unique isomorphism. They're uniquely isomorphic. There's only one choice of function between these two sets. And so, I want to understand what the singleton set is in a very specific way. So I said the empty set is the unique object satisfying for any other set. There's a unique function from the empty set to X. Here, I'll say that the singleton set is the unique set satisfying the following. The unique up to isomorphism set. Again, I'll use this notation of just like an asterisk inside of a set brackets, satisfying the following. So for any set X, there's a unique function from X to the singleton set. All right, this is like an alpha. Let me take it all right. Oops. All possible functions from X into the singleton set are just comprised of this one function. And all you have to do for this is just send every little element of X to that single point. Okay. So now what I'm going to do is give you exercise number 2. Is that in red? Yeah. Okay. So I want you to formulate this property. Formulate this in terms of an arbitrary category C. moreover, prove that this property uniquely defines this object. And prove it uniquely defines the object. So the singleton set is actually a more general example, or it's an example of a more general phenomenon called a terminal object. An object that every object maps into. Likewise, for the empty set, this is an example of something called an initial object. An object that maps into every object. And moreover, whenever they exist, they don't have to. They're unique up to isomorphism. Okay, so for exercise number 3, so we're going to work in a specific case. So for the category of vector spaces over a field, so pick any field you want, K. Is there an initial or terminal object? Is there an analog of something called the empty set in the category of vector spaces? We know that, for example, the empty set is not a vector space. So it can't be as simple as just transplanting the same example into vector spaces. So you have to do a little bit of work there. Does this mean it doesn't have one? That's a different question. Okay. Let's look at another type of example. So now I'm going to define, so let's do another example of partially ordered sets. Let X be a set with a partial order on it. So this is a poset. So if you want to look this up a little bit later, this is a partially ordered set, which is very similar to a total ordering on something like, the natural numbers or the real numbers, but you can't necessarily compare any two given elements. So a poset is very much like a tree diagram. So given any poset, I could turn this into a category. Consider this as a category in the following way. Category via, so my set of objects of this category are just the elements of the set X. And for any two elements of X, let's say little x and little y inside X, the set of morphisms between them is defined as follows. So hom X less than is defined this way. So I'll say that there's a unique function from X to Y if X is less than or equal to Y. And this is empty otherwise. Oops. It's just recording if X is less than or equal to Y. And this defines a category. If I have, say, 3 elements. So x, y, and z. And suppose x is less than or equal to y, and x is also less than or equal to z, but y and z are not necessarily comparable. So I'd write this as x, y is, this is I, maybe this is j. This is just that function I. From y to z, since they're not comparable, this is empty. From x to z is the function j. Oops. My j's look like a little bit like y's. That's really bad. J. A really popular example is as follows. Here you take any set, you can form the power set of x. So sometimes this is written like script p of x, or maybe it's written like 2 to the x. This is the set of subsets of x. Ordered by inclusion. Maybe partially ordered by inclusion. So this is an example of a pose set. This is the power set of x. Very important, nice thing. This is a complete Boolean algebra in any case. This is a complete Boolean algebra. I could take another really important example. Let X be a topological space. And I'll write OPX for the collection of open subsets of that space. And these, again, are partially ordered by inclusion. This is a really important example of a pose set. Comes up all the time in, for example, my own research. So this comes up all the time. In algebraic geometry. Where it helps you define something called a Grothendieck topology for topos theory, whatever that is. We'll get to that maybe in the 6th lecture. A Grothendieck topology. And so on. If you're really clever, you can turn any given pose set, or certain kinds of pose sets, into things that sort of resemble things like this. You can kind of consider a pose set to be a sort of topological object by looking at the similarities between these types of categories. It's actually a really neat thing. This is what category theory lets you do. It lets you sort of back away from the narrow confines of your given subject and see similarities with other subjects. Wow, this is a really bad handwriting here. This is Grothendieck topology. All right, let's see. probably going for about 45 minutes. So let's do a few more examples. I'm really bad at keeping track of time, especially when I'm talking to myself in an empty room. So I'm going to talk to you about monoids now. So a lot of you have just finished this group theory course with quantum formalism, so you know what a group is. You know it's a set with some nice operations. You always have the identity morphism, you have an inverse to any given element, composition is associative, and so on. A group multiplication is associative. A monoid is like a group, but you don't necessarily always have an inverse. Like groups, but without inverses. So, for example, while you might have the group of integers under addition, you'd have maybe a monoid of the natural numbers under addition. Right? Oops. So the difference now is that you can't necessarily subtract numbers off. You can't add negative numbers to any given number to undo an operation. So this is maybe a group. This is a monoid. Versus. So I'll leave it to you to maybe look up the definition of a monoid, but what it comes with is, so if I have M is a monoid, I have a binary operation on here, right? A way of combining elements of M. Maybe I'll write like asterisk as my monoid multiplication, my operation. And I have an identity element. I can say that E times X is equal to X times E equals X for any X in the monoid. I'm going to be obstinate and interpret this in terms of category theory, because that's what we're here to do, right? So I'm going to turn this monoid into a category. So this category will have only one element. So my only one element, one object, which I'll just write as M itself. I can think about this as sort of like a singleton object. And I turn every element of the monoid into a function, into an arrow here. And here I'll write the Homs, let me write this, bold. How do I want to phrase this? I've never seen a good way of expressing this, so maybe I'll write the objects of this thing. There's only one object. And the morphisms from this object to itself are exactly the elements of the monoid. So I'll express it as follows. So if I have, here's M, I can look at functions from this thing to itself, which are just monoid operations, right? This group operation here, or sorry, monoid operation that I've specified here is sort of like multiplication by the element X. Multiplication by X. Or monoid multiplication, because it's not really multiplication. And I can represent, let's say, my composition law in terms of this property. So if this is multiplication by X, this is multiplication by Y, then this is multiplication by Y times X. So in a precise way, you can actually reframe the following. So, example, a group, or maybe, okay, this is a really bad exercise. I think this is exercise 4 now. But I want you to make this precise. Part of this is being able to take the words of an unreliable narrator, a poor lecturer like me, and make this into a precise statement. Prove the following statement. Prove the statement. A group is a category with one element or one object where every arrow is an isomorphism. Every morphism is an isomorphism. It's kind of neat interpretation. So modify this thing to think about the difference between groups and monoids. It's not really, it ends up being simpler than it sounds. Okay. I've been waxing on for this, and I'll talk a little bit about some more examples maybe in the exercises, or maybe next class. And let's see. Oops. We should define functors. So I've specified a whole bunch of things about, I want to go back to this initial thing I wrote down. That was a while ago. I gave you guys this statement at the very beginning. To understand a structure, it's necessary to understand the morphisms that preserve that structure. So let's go a little bit meta. To understand categories, it's necessary to understand morphisms that preserve the structure of a category. Right? I want to understand functions between categories. So, what is a sort of structure preserving morphism between categories? Oops, I can't spell. Categories. So that is, if I have two categories, C and D, say C and D, what would it mean to define a structure-preserving function between these two things? So far, a category consists of a collection of objects and a collection of functions or morphisms. So what it should do is the following. It should consist of so F should define, or maybe composed of, a function. I should be able to take an object of F, of C, apply F, and get an object of D. I write it like this. But the important thing is I'm not just caring about the objects. I should care about the morphisms too. I should say for any morphism from X to Y, I should be able to obtain a morphism between F of X and F of Y. So this is in C, this is in D. These are my two important things. The function between objects and a function between sets, or morphisms. So what this really just, in fancy language, I should have a function between the set of morphisms from x to y to the set of morphisms from f of x to f of y. It should be a function. You should also write as sort of f. Maybe sometimes we write this as like f lower star. It depends on the subject. It should, again, these are my two main properties. It should satisfy some compatibility properties too. It should respect composition of functions. So if I have g of f, I should write this as f of g composed with f of little f. So it should respect composition. It should send identities to identities. So if I have the identity on x, it should be sent to the identity, on f of x. And this ends up being what we need. So we have these two properties, 1 and 2. They're the main deal. Like you think about it in terms of this. Then you have these two extra properties that are just kind of bookkeeping, making sure that it's preserving all the nice properties we like about these categories. And a structure preserving morphism between categories, we give this thing a special name, a very silly name. We call this a functor. And sometimes it isn't always really easy to, you get everything you like except for this property right here where you preserve composition in the right way. So we call this specific kind of functor a covariant. Covariant functor. Sometimes you get every property to line up except for this one, and what happens is that you get f of g of f goes to maybe the opposite way around. Oops. In that case, you still have a functor. We call that thing a contravariant functor. It's a contravariant functor. We'll see more examples of those in the future. Let's talk about some examples. These things are very, very common. So I once encountered a quote that was very poetic. I think it's by John Baez. So this is every sufficiently good analogy is yearning to become a functor. These guys are a little bit poetic, and it's kind of adorable. Sometimes category theory in this way, in an analogous way, is sometimes called the science or the mathematics of analogies. Cool. Okay. Let's give some examples of functors and then maybe call it quits for the day. And we'll pick up again next time. So Well, we have the dumb functor. We have, for any category, there's a functor that does nothing. Identity functor. Oops. Identity functor. So this is, again, maybe the identity on C. So it sends each object to itself and sends each morphism to itself. So that's not really interesting, but you can see really easily how this defines a functor. It satisfies all the nice properties. And it gives you the framework for looking at the category of categories, where your objects are categories and your functions or morphisms are functors between categories. This gives you the right framework to look at that. Okay. So let's define some other ones. I'm going to define a functor from the category of groups to the category of sets. All right, this is U. So what this does is it takes in a group. So G will be, it's a set with some kind of binary operation, and all this functor does is forget the operation. So this is sometimes called the forgetful functor. You should check why this actually defines a functor. But what this does is really reinforce the idea that groups are just sets plus extra operation. If you forget that extra stuff, you do just get a set back in a really fundamental way. Okay, now I'll go backwards. So I'll define a functor from sets back to groups. I'll call this free. So it takes a set S and spits out the free group on a set S. On maybe the set. Maybe I'll give this, all right, this is like a script F or something. So the free group is the smallest group that, or how I should say, maybe the best way of endowing a set with a group operation. You consider all kind of words on elements of the set S. So this is something I want you guys to look up. And if it ends up being something that is kind of unknown to most of you, then I'll go over it again in the problem session next week. So look this up. And if not, if hard, I'll talk about it some more next week. There's a really important property here between these two functors. These are somehow generalized inverses. So if I have group and set, these are, you can think about them as generalized inverse functors to each other. in fact, what they're called is an adjoint pair. They form an adjoint pair. Of functors. So we'll discuss this in a few lectures in more detail, but adjointness of functors is one of the most important concepts in all of category theory. It's one of your biggest tools you can have. So we'll talk about that some more. But I'll give maybe 2 more examples and then we'll be done. Okay. So, all right. So in the category of vector spaces, so we're looking at the vector spaces over a field. I have a really nice functor called the dual vector space functor. So it takes a vector space V and it sends it to the vector space, which I'll write as maybe V star, defined by the set of linear functionals from that vector space until the ground field, K. So I'll have to be a little bit careful here because this looks like it's well defined. I can send any vector space to this given vector space, but if I have 2 functions, if I have, V and W are vector spaces, and I think about, linear functionals from W to K and from V to K, the correct way to compose these things is backwards. Given F, the correct morphism goes the other way around. So, I'm writing this quick thing. This is the same thing as this. I'm just writing this as shorthand. If I have a linear functional on W, I can produce a linear functional on V by composing with F. So I take psi here from W to K, and I compose it with F to get a linear functional this way. By doing psi of F. Sometimes you'll see this as the push forward. Oh, actually I think it might be the pull back. I can never remember which way. Pull back along F. So what this actually does is it defines a function from the opposite vector space, or opposite category, into vector. It reverses the order of the morphisms. So this is my dual vector space. Functor. Okay, so what I want you guys to do for an exercise is the following. I want you to understand, describe, composing this functor with itself. So I want to do the double dual functor. Functor of the double dual. From a vector space to itself. or rather from the category of vector spaces to itself. So this is, you take a vector space and look at the dual of the dual of V. So this is this. It looks a little unwieldy, doesn't it? Oops. And describe its relationship with the identity functor. How are they related? Are these two functors the same morphism? I'll describe this more in the problem session next week. I'll put out a message on the Discord channel to see when is the best time for you guys to meet for the problem session, but the goal is to probably have the problem session for the first one. So first problem session is going to be next Sunday. And this will be a live problem session like the Crowdcast Q&A was, where I'll be around, where we can talk about the lecture, we can talk about the problems or any other examples. Maybe I can give some more examples that we didn't talk about today. And I'll put up on a post out on the Discord channel to see when is the best time for you guys to meet. And I'll put these problems up on the GitHub repository for quantum formalism in the category theory folder. And we'll talk more next time, guys. This is a lot. The power of this stuff is in the examples and understanding how it fits in with things you already know. Category theory is everywhere, and we're trying to take over the world. All right. I'll see you guys next time.